instructions in front of you here. So in fact, let's make sure we have that squared away right now. So in the examples that I did last time, they are in the examples directory underneath this date, the April 15th date. And I think we were just working with simple thread last time. Let me open up the make file and show you what the make command looks like. So it's G++ and then the name of my source file, simplethread.cpp. And then there's this funny flag -L boostthread-mt. That is required to access the boost libraries. And different boost libraries require you to link against different files. We're using the thread library, and that suffices to get access to the thread library.
Are all of the library references of the form -L_boost_?
So the -L is actually a flag to G++. -L is a message to G++. And what it says is whatever follows -L is something that I would like you to link to this executable. So the boost thread-mt is a bunch of precompiled stuff. All these precompiled functions, and you compile your guy, and then the -L says now glue it to this other guy and give me an a.out. And they're actually all, if you go to user lib, it might even be, yeah, user lib. There's all of the boost libraries. I just installed all of them instead of the threaded ones. Instead of just the thread ones. So you see, remember yesterday I sort of slowly went down the whole boost library and we saw what was in there. Every sort of major piece of boost has its own collection of stuff associated with it that you would have to link to in order to use it. And then there's the whole statically linked versus shared libraries, which we won't talk about. So they're all in there. There's thread down there, and there's thread-mt. All right. So if you put your make file together like that, then make suffices. And if you don't feel like doing a make file, then this is the command that you need to successfully compile. If you try, the order matters. I found this out the hard way. If you try to do something like G++ -L boost thread mt and then simple thread, you'll get a bunch of errors. So the -L comes at the end. If you're using more than one of the boost libraries, you can have multiple -Ls. -L this, -L that, -L the other thing. If you look inside, the other part of this is to include the header files. The boost library uses .hpp. It's a header file for C++. I don't know why they use that notation. And if you want to use the thread library, you have to include thread.hpp. But notice we use angle brackets instead of double quotes. That's a signal that this is an installed library. It's out in the official system location, and you can find it there. The official system location is user include. And all of the header files that you would possibly want to include are in here. Some of them are in subdirectories. So there's now a boost subdirectory, and all of the header files for boost are in there.
Oh, so if we were ever installing libraries, this is where we would put that.
If you install libraries manually, they should go into a place called user local include. And this is a Unix paradigm that goes way back. So if you're installing a library that comes from an official source for your operating system in Unix, then those libraries will get installed in user lib and user include. The binaries will go into user lib and the headers will go into user include. If you're compiling a library, you went out and got the source code and you're compiling it, installing it yourself, then it should go in user local lib and user local include. Local is a name that's used to suggest that this is something that I've done locally to this particular machine. This is something that I did to this machine. It wasn't from some official source. So when you're mucking around with Unix, that's a big idea. And fortunately, to the compiler, it's smart enough to know to look at user local lib and user lib, and it's smart enough to look in user include and user local include. So you don't have to muck around with it that much. But and most third-party source code is going to, by default, install itself under user local instead of user. Okay, some technical details, some Linux/Unix customs. Let's go back into the example directory. Last time I ran this program, in fact, let me run it again. Okay, so this was the one where each process was sleeping a certain number of seconds that was associated with its process ID number. I ran 8 threads. The first thread slept a second, the second thread slept 2 seconds, and so on. We saw how that works. We talked a little bit about this thread object. So I'm using the thread constructor to build a bunch of threads and send a function to each of those threads. And I have an array of threads, and then we talked a little bit about join. Join is for the purposes of synchronization. When you call a join on a particular thread, it will hold the program execution until that thread exits. Synchronization is really an important issue. One of the big problems, or not problems, but sort of the things to think about with threads is you don't know which thread is doing what at any particular time. You've assigned a task. You've assigned a task to all 8 threads, but you don't really know, relatively speaking, which one is doing what when. And if these threads need access to shared variables, for example, cout is an output stream object, right? And it's a global variable. People don't really think about it, but it is. It's a global variable. You use cout in main. You use cout in various functions that you're writing. You never really declare cout, right? And yet it's there. And that's because it's defined globally in the IO stream header. So you've got this global variable, and you've got these functions all running on different threads that all want to print their message to the screen. What happens in the unlikely event that both threads want cout at the same time? To be honest, nothing in this particular case is going to happen because the likelihood of that happening is almost 0. But probably if it did happen, you would just get some sort of segmentation fault or whatever. But you could probably run this program with 8 threads 1,000 times without being careful and not get a segmentation fault. The philosophy is that you should be careful when using shared resources, and the threads library provides a way of being careful, and that's with what are called locks. So you'll notice up here I declared a global variable, a mutex. Mutex stands for mutual exclusion. Mutex. And I declare this variable. It's a very mysterious object. It has a couple of member functions in it. It has a lock member function and an unlock member function. Between lock and unlock, the thread has exclusive access to the shared resources. So between the lock and the unlock, the thread has exclusive access to cout and can safely use it and send stuff to it. And it will lock all of the other threads out from using it until it's done, until you call the unlock. And one of the most common errors in parallel programming is forgetting to unlock. And it's really, for complicated programs, it's really a terrible thing to try to debug. So you've got all these complicated variables flying around, and you've locked some of them, and then this other thread wants it. That other thread will sit there forever waiting for the resource to unlock. And you won't really know why. Now, debuggers are getting pretty good with parallel programming, and we don't use debuggers in this class, but if you were sort of a production line code monkey, you would have a debugger, and you would know how to use your debugger, and you would know all of the sort of tools available to you for analyzing parallel algorithms. And one of those tools would be, here's all the locks that are going on right now while you're running your program, and you see this lock right here, it's really persistent. Maybe you should look at that one and see if you forgot to unlock it. So that's the idea with lock, and you should use it whenever you're accessing shared resources. Okay, go ahead.
The way that's declared right there, it's because what we're locking essentially is the cout, that we don't want two things trying to use that at once. When we just say, oh, so it's the IO at the beginning saying, oh, never mind.
It's not saying anything. I could have called that thing Fred.
Yeah.
Okay.
So then does it just lock everything?
Pretty much. Any kind of assignment or insertion is going to be blocked.
Okay.
Really, any kind of modifying action is going to be blocked.
On the entire hardware?
Pretty much, yeah. Right? So while that lock, as brief as it is, while that lock is on, nobody else can hit cout.
Or like if you had other variables too, those would be locked as well.
Exactly. Exactly. But if there happens to be a local variable between a lock and an unlock, that's not going to have any impact. It's smart enough. I mean, it's not even really smart. It's not. It won't have any impact. It's just these shared objects that are restricted. So how does this work? Well, these threads, while they're running, they're constantly looking at this table of locks. And if it's in the table, then it'll just wait until it's not in the table. And so if you have other like local variables in there that are locked, the other thread's never going to look for that particular symbol because it's local to that thread over there. So you can have other stuff between the locks. That's my point. You can have other stuff between the lock and the unlock. You don't have to worry about it so much. You could just like lock the whole body of the program, but if you lock the whole body of the program, then you might as well just do it serial, right? That's effectively right. If you lock the whole parallel thread, like as soon as the left curly brace you lock, and then the right curly brace you unlock right before that, you might as well just be doing serial programming.
Right.
Okay.
So I imagine there's like a more precise way to do this.
Yeah, in fact, I came up with an example of I think a fairly illuminating example of where and how to lock, and maybe locking too much and how it would cost you. So, but let me go on with another example first. I want to do an example where each processor gets a chunk of a larger array, because after all, that's where we're headed. Each processor gets a chunk of a larger array and just puts its process ID number in the array. So let's do that. Okay, so here's the same guy that we had before. And what I'd like to do is sort of walk you through the steps of modifying this hello world guy so that instead of just printing out the process ID, instead it's going to receive a piece of a larger array and write its process ID number in every slot in the array. So there's a couple things we should do first. Let's do, I don't know, PID array. Let's call it PID array. So if we change the name there, we have to change the name down here in the bind command. And what kinds of things do we want to pass to this array? Well, we would like to pass the process ID number. We would like to pass an array of some indeterminate size. And of course, we have to tell it, I guess we have to tell it how big that array is. So let's do that. Yeah, we certainly do. So I'm going to pass these three arguments. What does that look like down here in bind? We just add a and n, and we better declare them. So int a. I'm going to use something that's divisible by 8, but that's not too large. So let's try 24. And let's do n equals 24. So we have this array. Let's go through and initialize it to 0. Okay. That looks good. We should think about what part of the array each process ID number is going to deal with. So let's look at that over in the notes. So we've got this array, and we've got 8 processors. So that implies that we should chop it up like this, right? And what I want is a formula for the indexes that a particular process is going to be dealing with. So I guess the first thing we should ask ourselves is how many elements are in this chunk? N divided by 8. I'm going to let P be the number of processors. So let's come up with a formula for the first and last index in the first chunk. Or not a formula. What's the first and last index in the first chunk?
0 and n divided by p minus 1.
So the first chunk is 0 up to n divided by p minus 1. And the second chunk? N divided by p to 2n divided by p minus 1. And the kth chunk?
K minus 1 is n divided by p up to k n divided by p minus 1.
Yeah, I'll buy that, k minus 1. And k goes from 1 up to p, I guess. K goes 1 to p. So let's see if that works. Let's see if our formula works. When k is equal to 1, looks good. When k is equal to p, looks good. This turns into n minus 1, right? Which is what you want, the last element of the array. So there's a nice formula for distributing the chunks based on PID. Let's go back to the program here. I'm thinking we should pass in the number of processors. And then we could actually replace all these 8s down here. With just num threads. All right, so the goal here is to write ID into this thread's chunk. Write the ID into this thread's chunk of A. All right, let's get a local variable, call it h, and let's do n divided by num threads.
Instead of exposing the entire A array and then passing in the number of threads and letting the PID function calculate what chunk is it, why not just take out the little chunk of A that's associated with that thread and pass in that small chunk?
Right. I mean, one way well, there's a couple reasons why I want to pass the whole array in, and that's because I don't want to make copies of memory. I want this.
You can just pass in the pointer to the start of the
Right.
chunk.
There are 1,000 ways of doing this. Let's just do it right in this more direct way, and then we'll talk about using pointers to do this. You make a good point, though, because when you do your parallel sort, I'm going to show you a trick where rather than writing a parallel sort that sort of needs a starting index and an ending index, I'm going to show you a trick where you just create a pointer that points to the start index and knows how long the chunk is, and then you don't have to mess around with indices a whole lot. But for now, we're just going to sort of bull ahead and do this in perhaps an intuitive way, but maybe not the slickest way. So this h here essentially represents the chunk, the size of a chunk of this array. Agreed? So it's the size of the array divided by the number of threads. The starting index, we just got a formula for this, right? So it's going to be the ID times h is the starting index. Yeah? And the ending index,
Wasn't ID minus 1 times h?
I don't remember. How are we doing IDs here? Yeah, p plus 1. Okay. You know what? I'm going to go 0. I think I'm going to go 0 justified here. I already did the formula in the notes, though. We'll keep it this way. I think that does it. So I'm now computing the start and the end indices. These are the indices that this thread, this is the range of indices that this thread is allowed to deal with. All right, so now we just have a simple for loop for, let's grab another index variable here. For I equals start, I less than or equal to end, I plus plus, AI equals ID. Now that's the question, do I want to lock this?
No, because they're never accessing the same data.
Exactly. If I had to lock this, I'd be in trouble. I would never be able to realize any serious gain from doing threaded programming if I had to lock this kind of access to the array. It's up to the programmer to make sure that the threads aren't competing for the same variables. And by partitioning the array in the way that I have, I hopefully have assured that I'm not having two threads access the same array index. Okay, so we initialize this guy to 0. we launched a bunch of threads, we joined a bunch of threads. Let's print out the results. Grr. And let's hope this compiles and runs. Okay, so somewhat convincing that we actually did what we purport to have done. What we see is triples of PIDs, 111, 222, 333. I guess I should prove to you that they actually started out as zeros. So let's put that up there. And maybe we could change the number of threads to 4. So if we change the number of threads to 4, we should see collections of 6 PIDs, but only ranging from 1 to 4. Okay. And no locking was required here, because even though it was the same array, we were only accessing disjoint sections of the array.
What if we wanted, let's say we were writing our program when we're trying to trap errors and things like that, and we want to see out within our function there, we would have to log to that.
Right. Let's do that. Let's print some debugging messages. So this is thread ID. And maybe we'll print out the starting and the ending coordinates. It's a tab. And this will show us how the threads have been partitioned. Of course, we better lock because we're using a shared resource now. Yeah. So here are some debugging messages from the 4 threads. And you can see the indices that each thread was tasked with. And of course, they're not in order because we can't really control the order in which threads are executed. Questions about that? Okay, so that's a little bit more interesting example because this array was modified in parallel. And that's not something that we've been able to do before we started using threads. Okay, let's go on to the next example then. So what I would like to do now is generate a random... Oh, I want to do one more thing. This is sort of a side issue. What I'd like to do is make this numthreads argument a command line argument. And let me show you how to do that because it's something that I mentioned in the homework assignment. So we'd like to be able to say a.out4, and it'll run this program with 4 threads. The way to do that is to use the argc and the argv elements. We've talked about that in here, right, with the hzip stuff. Okay. So let's do a bit of a reminder. So we'll do a little bit of error checking first. If argc is less than 2, then I want to just print out a usage statement. And what this does is it reminds me, if I try to run it, that I need to do that. I need to specify the number of threads. Remember what argc is. This is the number of distinct arguments on the command line, including a.out, or whatever the name of the executable was. So if argc is less than 2, clearly the user was missing a piece of information on the command line, and you don't want to continue. If you make it past this check, what you would like to do is take that second argument and turn it into an integer and set it into num threads. There's a built-in command called a to I. Can you guess what that stands for?
Array to integer.
Close. ASCII. ASCII to integer. ASCII to integer, and it's almost built in. You have to include C standard lib, I think. Let me see. Nope, it's built in. Different implementations do different things, you know, about what's automatically included and what's not. And apparently, that's built in. So you've noticed now that I've replaced the num threads variable with the ASCII to integer conversion of argv1. So now I can provide the number of processors on the command line.
argv1 is an array of characters, right?
argv1 is a C-style string, yes, an array of characters, a null-terminated array of characters. Yes.
So would argv0 also be null terminated?
Yes. And so what do I mean by null terminated? So when I feed that 8 in, right, it comes in as an 8 and a 0 byte. And C-style strings are more than just an array of characters. What makes them a C-style string is they have that 0 byte at the end that indicates the end of the string.
So that's why typecasting wouldn't work.
It's why you have to be careful if you're just jumping back and forth between character arrays and C-style strings, because the character array will not have the 0 byte at the end. And if you want it to play nicely with stuff like a to I, then it has to be null terminated. Fortunately, the argv and argc mechanism produces null terminated character strings. So we've got some nice functionality here with argv and argc, and in fact we could go one step further and actually set the problem size. I won't do that, but we could set the problem size from the command line as well. Okay, now let's look at the next example. So let's, instead of having these things do kind of toy problems, let's do a real parallel algorithm. And by that I mean, let's see if we can sum the elements of an array in parallel. This is not something that you think about as needing a parallel algorithm, but if you do it correctly, you can get scaling, right? So you have an array of integers, and you'd like to add them up. The standard thing to do would just be to, in your main program, you build an accumulator variable called sum, and you just go through and you just add the elements of the array to the sum variable one at a time. Well, that's actually parallelizable, isn't it? I can take a sub-chunk, hand it off to a processor, add it up, and then dump it into the accumulator, and actually save time. You'd be hard-pressed to measure that time savings, but you could do so.
Ooh, a really big array.
Yeah, really big array is what you need. So let's see where we are here. I'm going to copy, I think I'm going to copy that other guy. On top of this guy, just so we have a continuous collection of examples here. So this is where we left off. Instead now of writing my PID to my chunk, what I want to do is add my chunk up. So let's change the name of the function to something like sum array. And don't forget to change it down here. I don't know, maybe I'm jumping ahead here, but can you think of how we might do this?
Say before passing the right chunk, return an integer, create a local some variable, sum it up.
That's one way to do it. Could I do it so that when these processes exit, I have no further work to do?
The global sum variable.
Not even quite global per se. I just need to be able to pass it in from main. Pass it in by reference. So I could have a variable in main. Let's go down in here into main, and let's call this guy psum. P for parallel sum. And what's going to happen inside each thread is when each thread is done computing, it's going to take its local sum and add it to psum. And it's going to do so in a locked environment. And then when you're done, because you passed psum by reference, when you're done, psum will have collected all of the subsums and will have the sum of the full array. Let's see if we can make that happen. What I'd like to do to make this a little more interesting is just fill the array with random numbers. Let's do rand %10, say, just to keep it simple. And let's do some time seeding. Oh, I already have seed time in there, good. So I'm just going to fill the array with random digits, 0 through 9. And what I'd like to do is sum those guys. I'll print out the array here, and in fact, why don't I even compute the sum? So let's get another sum variable here, sum, and all right, so we fill the array with random digits. I'm going to show you the array, and I'm going to show you the sum. Stop me if you see me make a mistake, but I think we're good up to this point. So this is sort of just a check to make sure that our parallel sum is working. Let's see, what arguments do we need? Well, luckily we've already done the work so that this guy knows what its starting and ending indices are. So let's play around with a couple of things here. Oh, I better I better get myself a psum. Let's go down here. Psum. So ostensibly, when I'm done, the variable psum will have the global sum. I'm going to print out the data again and print out the sum, I guess. Okay, my arguments match. I've got everything initialized. Let's go up in here. Start and I. I could do something like this. What's wrong with this? It's not locked. So how do I fix that? Exactly. So I can't just put locks around this. I mean, I could. But then I've destroyed all the parallelism. While this thread is doing its sum, everybody else is waiting. So the way to resolve that is what Evan just suggested. I should get a local variable and do a local sum. And then what?
Lock add local sum to
Right, so psum plus equals local sum. That lock I need, but that's presumably a less onerous lock, right? That's one brief lock for one addition, and all the other additions happened in parallel. Okay, and this is the bug that I was struggling with this morning, or not a bug, feature, I don't know. It didn't work, and it should have. At least by appearances, it should have. Passing a variable by reference to a thread, it turns out, it's not enough to make it a pass by reference value up here in the function. You actually have to go an extra step and tell it that this is a pass by reference variable. So that's a built-in function to, boost bind. Boost bind. Maybe it's boost ref. Now I can't remember. We'll just see if it works. No, it's got to have bind in it. Or not. Okay.
You already have a bind.
There we go. So yeah, just ref is fine. So that must be a lower level. It's part of boost rather than boost thread or boost bind. So took me a while to figure that out this morning. Hopefully it won't take you any time to figure it out, because I just told you. Run this guy again on, say, 8. And it still works. Questions about that?
The way this works, obviously there'd be no point to doing it, but it would still work even if you put like 10 in for the number of threads. Would it just run one thread and then like wait and then run another thread on the same process? Like,
okay, if I put in 10, my formula for start and end breaks.
yeah, that's
So I've got to be more careful. That is not an insurmountable problem. What you want to do is find out essentially the remainder after division of p minus 1, and then you'll have a nice divisible chunk of stuff for the p minus 1 processors, and then take the remainder and send it to processor p. So it just requires more work, and that's why I said, you'll see this in the literature a lot. Right. Let me be clearer. Let's say I have 10 pieces of information, and I have 4 processors. What I'll do is I'll take if I go 4 into 10, how many times does 4 go into 10? 2 with 2 left over, right? So I could take I could take the two jobs, the two pieces of data to the 4 guys and deal with 8 pieces of data. And then when those guys are done, I could do the 2 more. Okay? Or I could look at 10 divided by 3, right? 10 divided by 3, that's chunks of 3. Let 3 of the guys work on chunks of 3 while 1 guy works on 1. That guy's going to finish early, but it might be better than doing 4 2s and then 1 2. In fact, it almost certainly, it depends. You'd have to work on the timing. Do you see what I'm getting at? So it's really a question of how do you want to deal with that remainder when things don't divide evenly? Do you want to do the remainder after the full problem is over, or do you want to just have one thread do a little bit less work?
And from a technical standpoint, is there a problem with assigning more threads than you actually have processed?
There's not. I can run this on 24 threads if I've done my arithmetic correctly, and it'll work. Let's try it. See if I've done my arithmetic correctly. Yeah. So 24 threads. It's just that some of the threads landed on the same core. Other questions? I would encourage you to play around with these examples in this evening while it's still fresh. This is definitely a new way of thinking when you're programming. And play around with it. See if I can do this. See if I can do that. For example, maybe go home and see if you can add 1 to every entry in the array, or add the PID to every entry in the array in parallel. Just tweak it and see if you can make stuff work. And then we'll talk a little bit more next time about, we're pretty close. This is actually not a bad place for you to start, because if I want to do a parallel sort, how can I tweak this thing?
I just sorted the chunk of the array
Instead of adding them up, sort them. Right? And you have lots of options for how you want to sort them. You can use bubble or quick or merge or whatever. And you can just write another function, call it bubble sort. And you can call bubble sort inside of the sum array function. And you don't have to do any of that crazy bind stuff. That's all going to work just fine. The only time you have to worry about the binding is when you're actually passing that starter function into the thread. That's when bind works. But once you're in the thread, all the normal rules of C++ apply. And if you have another function called bubble sort, you can call it in there in exactly the same way that you would in a regular main function. So you're actually pretty close here. If you do that, then what you're going to have is a bunch of sorted subarrays. And the only question that remains is, how do you get the sorted subarrays, which may be out of order, not only out of order, but there may be, certainly the whole array won't be sorted, just little subchunks will be sorted. How do you get from the subchunks to a fully sorted array? And that's called merge. And we'll talk about how to do the merge on Friday. Until then.